In this question, we've been given a discrete random variable x, which has a probability generating function as shown. So k times 1 plus t in brackets to the power of 7. We're told that k is a positive constant, and we're asked to state with justification the least and the greatest value that x can take. In general, the values that x can take is going to be the powers or the indices on each of the terms in the expanded polynomial. The powers of t will indicate the x values that the distribution can take. Well, looking at this probability generating function, the smallest power of t would be t to the 0, we would get a constant term, while the largest would be t to the 7. So there we have it. We have the minimum and maximum powers of t, indices on t, and therefore the minimum and the maximum values that x can take. Part B of the question asks us to state the name of this distribution, fully specifying any parameters. Well, looking at the brackets, I hope you recognize straight away, this is a binomial distribution. We have two terms inside the bracket, and it's being raised to a power. This is a binomial distribution. The power that we have is going to be n. So that's the maximum number of successes. That's the number of trials. N equals 7. What is the probability of success in this binomial? I'm looking at the two terms, the 1 and the 1t. Well, the coefficient of t would usually represent the probability of success, while the constant term would be the probability of failure. At the moment, both of those are equal to each other. But we know the probability of success and failure are not both going to be 1. Only when we factor in the k would we be able to see those coefficients directly. But because I've recognized they're the same and they must add up to 1, I recognize that actually the probability of success must be a half. Could do it the long way, but I recognize it's going to be a half because the probability of success and the probability of failure must be the same number. So we have a binomial distribution where n equals 7 and p equals a half. Let's just define that fully over here. In part C of the question, we're asked to determine the value of the probability that x equals 5. Well, now that we know it's a binomial distribution, I can just calculate with the binomial rather than the probability generating function. So for the probability that x equals 5, we can use BCD with the minimum and maximum being 5, n is 7, and p is a half. Into our calculator, 0.1641. Part D of the question asks us to use the probability generating function to calculate the mean and the variance. Okay, the probability generating function. And there are some notes here just to let us know we wouldn't get any credit if we obtained the mean and the variance any other way. We can probably find the mean quite easily from the binomial distribution, n times p, and the variance, n times p times q. But here we're being asked to use the formal techniques. Here we're being asked to use the probability generating function techniques to find the expectation and the variance. Firstly, let's consider the probability generating function that we have. So, as I said before, there's a coefficient of k on the outside, and then we have this bracket that we know has a binomial expansion. We can actually rewrite this and figure out what k is going to be. Because we know this is a binomial distribution where p equals a half, we also know that this probability generating function could have been written as half plus half t to the power of 7. Okay, if we were to take that into the original form, we would need to factorize out the half. When we factorize out the half, it needs to come with the power of 7. So on the outside, we would have 1 over 2 to the power of 7, and then these brackets. That lets us know that k is actually 1 over 2 to the power of 7. That's the value of k. Let's go for the expectation. The expectation of any probability generating function we can get if we were to differentiate the generating function and then substitute in 1. Let's find what we get when we differentiate. So we'll bring the power down, and that's a new coefficient, and we'll reduce the power by 1. So let's see what we get when we substitute 1 into this expression. That will get us 7 over 2 to the power of 7 times 2 to the power of 6. And actually, because I can see what's going to cancel out here, I know that we're left with 7 over 2. Now, I'm confident to see that because I knew from the binomial I should be expecting 7 over 2. To find the second derivative, we're going to go ahead and differentiate again. This time 6 comes down and it's a power, and then we've got the 1 over 2 to the 7, 1 plus t to the power of 5. Okay, so similarly, we're going to get 42 times 1 over 2 to the 7 multiplied by 2 to the power of 5. I can still see things will cancel out nicely, and we get 42 over 4, or 21 over 2. Let's not forget, the expectation of x squared is a combination of the second derivative and the first derivative added together. The variance of x is going to equal the expectation of x squared minus the expectation of x squared, which gives us this combination. Now we have all of these components. Let's just substitute them in. So we've got 21 over 2 plus 7 over 2 minus 7 over 2 squared. And that leaves us with 7 over 4. Once again, from the binomial distribution, this is what I was anticipating for the variance. Just making sure you're very comfortable with these techniques, expectations and variances being calculated using the standard technique for a probability generating function.